Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, that you're looking up at the night sky.
Oh, always a good place to start.
Right. And if you picture those incredible high-resolution images of galaxies, the big, majestic spiral ones.
Like the Milky Way or Andromeda, yeah.
Exactly. You see these massive, beautiful, swirling shapes. And we know they spin. We've known that for a very long time. But the real question is why?
Yeah, why did they start spinning in the first place? It's a huge question.
It is, because today we're going on a mission to trace that rotation, the spin of the galaxies we see right now, today, all the way back to the actual dawn of the universe.
Uncovering how primordial gravity basically, permanently fingerprinted the cosmos.
Which is just wild to think about. I mean, we're taking on a journey that bridges the gap between this unimaginably ancient universe and the galaxies existing right above our heads right now.
It really is a monumental shift in how we understand astrophysics. We're moving from this strictly observational science where we just, catalog what's up there in the sky to treating the entire observable universe as this single massive forensic crime scene.
A crime scene that's 13 billion years old.
Exactly. We're looking at the kinematics, the intricate rotational velocities of the gas within these galaxies, and using that to reverse engineer specific microscopic fluctuations that existed right after the Big Bang.
So the thread connecting the Big Bang to the galaxies we see today is spin.
Right. Angular momentum.
Angular momentum.
Yeah.
And if you think about the iconic shape of a spiral galaxy, that rotation is its most defining characteristic. But the actual mechanism that gave them that initial, that push, that torque.
That has been one of those incredibly stubborn astrophysical puzzles. It just sat there half solved for decades.
Why only half solved?
Well, the math worked in theory, but the observational proof was always completely obscured by the sheer chaos of billions of years of cosmic evolution. The prevailing framework for this is called tidal torque theory. It was formalized back in the late 60s.
By cosmologists like Jim Peebles, right?
Right, yeah. And the core idea there is that a galaxy's angular momentum wasn't generated from inside itself while it was forming.
Wait, really? It didn't spin itself up?
No. The theory says it was entirely imprinted on the precursor material by the gravitational tidal fields of the surrounding universe, like long before the galaxy even collapsed into a galaxy.
Okay, we need to break that down.
Yeah.
Because if you're used to regular everyday physics, that is completely counterintuitive.
Oh, absolutely.
Because in standard physics, gravity just pulls things together. It's an attractive force.
It pulls things straight toward the center of mass. Yeah.
Right. So if I have this vast cloud of gas and dark matter, and it starts gravitationally collapsing under its own weight, shouldn't everything just crash straight into the middle?
You would think so, yeah.
You just end up with a dense, non-rotating spherical blob. Gravity doesn't have a steering wheel. It shouldn't be able to induce a spin.
That's spot on. Radial infall conserves whatever angular momentum is already present, but it can't just create it out of nowhere.
So if it starts completely still, it ends completely still.
Exactly. A static, dead sphere. And the mistake a lot of people make here when they try to visualize this is the water going down a drain analogy.
Oh, yeah. I was actually just thinking about that, like how water swirls down a bathtub drain.
Right. People assume there's some kind of inherent vortex dynamic in space-time or a central sinkhole pulling matter in a spiral.
But there isn't a drain in space.
Exactly. There's no basin. There's no fixed gravitational well waiting to catch everything. And there's definitely no Coriolis force operating on the scale of the entire universe.
So if there's no drain, where does the spin come from?
It has to come from the outside environment.
Yeah.
During the very early linear phase of structure formation.
The primordial universe.
Yes. We have to look at the exact geometry of the universe back then. Specifically, how the dark matter was distributed.
And it wasn't a perfectly smooth distribution, was it?
Not at all. It was filled with these tiny density fluctuations, just regions where the dark matter was a tiny bit more dense than the space around it.
Uneven clumps, basically.
Uneven clumps pulling on their neighbors, So instead of perfect spheres collapsing in isolation, you have a highly irregular lopsided mess.
Lopsided clumps of dark matter and gas.
Yeah, the mathematical term is triaxial ellipsoids. But basically, think of them as massive, asymmetrical cosmic potatoes.
Cosmic potatoes, I like that.
And crucially, they weren't alone. They were embedded in this vast cosmic web of other growing overdensities, filaments, and massive empty voids.
Okay, so paint this picture for me. You have a lopsided asymmetrical mass of dark matter.
Right.
And a little ways away, you have another massive clump.
Yep.
So because gravity obeys the inverse square law, the gravitational pull from that neighboring clump isn't going to be uniform across our first lopsided potato.
Exactly.
The side that happens to be pointing toward the neighbor feels a slightly stronger tug than the side pointing away.
That differential pull, that uneven tug, that is the tidal field.
Oh, I see.
The neighboring mass is exerting a shear force across the entire spatial extent of the proto-galactic cloud.
Okay, let me try an analogy here. Tell me if this works.
Go for it.
Imagine I'm standing on a dock, right? And there's a big floating wooden raft out on the lake.
Okay.
If I tie a rope to the exact center of that raft and pull, the raft just moves straight through the water toward me.
Sure.
But if the raft is awkwardly shaped and I tie the rope to like one of the front corners instead.
I see where you're going.
Yeah. My pull doesn't just pull the raft forward anymore. That lopsided tug forces the raft to instantly pivot and rotate as it moves.
That is exactly the mechanism. The external gravitational tidal field exerts a torque on the lopsided mass distribution.
So the neighboring clumps of dark matter are pulling on the corners of the raft.
Basically, yes. And because the universe is expanding during this phase, this proto-galaxy is physically growing, but it's also being continuously torqued by its neighbors.
It's inheriting a spin from the unevenness of the universe itself.
It's gathering angular momentum from its neighbors, yeah.
And astronomers have been confident in this idea for a long time, right?
Yeah.
It's very elegant.
It is. It's mathematically rigorous. But proving it, that has historically been incredibly difficult.
Because it happened 13 billion years ago.
That, and because a galaxy doesn't just quietly spin in isolation for 13 billion years.
Oh, right. Galaxies smash into each other.
Constantly. You have major mergers where two galaxies collide and completely randomize all their stars. You have supermassive black holes blowing out jets of material, supernovae throwing everything into chaos.
It's just eons of cosmic chaos.
The entropy is staggering. Trying to find the original primordial spin in a modern galaxy is worse than looking for a needle in a haystack.
So how do you prove it? If the evidence is billions of years old and totally scrambled.
You have to find a way to reverse engineer the universe.
Which brings us to the breakthrough research we're diving into today.
Yes. Published in Nature Astronomy in 2026 by a team led by Mingji Sheng at Samyang University.
And they use something called the elusive project.
The elusive project, yeah. It is absolutely mind-blowing. It reconstructs the distribution of matter in the early universe based on the positions of the galaxies we can see today.
Okay, I have to stop you there. Because I'm sure our listeners are thinking the exact same thing I am.
What's that?
How on earth can they possibly know what forces existed back then just by looking at where galaxies are sitting right now?
It sounds impossible, I know.
I mean, isn't that like looking at a puddle of water on the floor and trying to guess the exact shape of the shattered glass it stole from?
That is a fantastic way to put it. And yes, it is exactly like that, which is why the elusive project is such a massive computational achievement.
So how did they do it?
Well, they didn't just look at where the galaxies are. They gathered massive amounts of real physical spin measurements from a huge sample of galaxies in our nearby universe.
Using specialized instruments, right?
Right. They used integral field spectroscopy. Instead of just taking one reading for a whole galaxy, these instruments use fiber optic bundles to take hundreds of independent measurements across the entire face of the galaxy all at once.
Wow. So they aren't just getting one general spin speed. They're mapping out the specific motions of the gas and stars within individual galaxies.
Exactly. They map the velocity field locally. The gas moving toward the telescope shifts blue. The gas moving away shifts red.
Doppler shift.
Yep. And from that, they extract the exact angular momentum vector, the precise spin of the galaxy today.
Okay, so that gives them the puddle of water on the floor.
Right. The modern-day measurements.
Okay.
But to get the shape of the shattered glass, ELUC takes the present-day massive structures, the big galaxy clusters and the empty voids around us, and runs the clock backward.
Literally rewinding the universe.
Computationally rewinding gravity. They take the messy modern universe, apply a massive smoothing filter to average out the chaotic small-scale stuff like recent galaxy collisions, and focus strictly on the large-scale underlying dark matter architecture.
Because the really big stuff, the massive web of dark matter, hasn't been completely scrambled yet.
Exactly. It's too big to have mixed chaotically. So they can run those large-scale structures in reverse, back to the Big Bang, and reconstruct the exact primordial density field for our specific pocket of the universe.
That is just, it's wild. They built a time machine out of math.
They basically did. And from that simulation, they calculated exactly what the primordial angular momentum should have been for any given dark matter clump before the universe got messy.
So they have the theoretical predictions from the early universe on one hand.
And the real-world, modern-day spin measurements on the other.
And they had to compare them.
Right. And the results they found were startlingly specific.
This is the crazy part. When Sheng's team compared the elusive predictions with the real-world measurements, where did they find the strongest match?
They found it in the gas within large, massive elliptical galaxies.
Okay, I have so many questions about this. Why just the gas? And why massive elliptical galaxies?
It's very counterintuitive.
Yeah. Because if I'm thinking of a galaxy that looks like it has a pristine, perfectly preserved spin, I'm thinking of a spiral galaxy. They are literally shaped like a spinning wheel.
Most people assume that. Spiral galaxies are defined by their rotation. But the data showed that spirals actually have a very weak alignment with their predicted primordial spin.
Wait, really? Why?
Because spiral galaxies are constantly pulling in new gas from random directions in space. Over billions of years, all that randomly falling material constantly shifts and tilts their rotation axis.
Oh, so their spin gets overwritten.
Exactly. The local environment overrates the primordial memory, so the spiral galaxies were out.
Which leaves the elliptical galaxies.
Yeah.
The ellipticals were essentially cosmic train wrecks, right?
Totally. When two beautiful spiral galaxies collide and merge, they destroy each other's organized disks. The result is a massive elliptical galaxy, which just looks like a giant, featureless blob of stars.
So a lot has definitely happened to these galaxies over billions of years. How could a massive, chaotic collision preserve a primordial spin better than a quiet spiral?
Well, this is why the distinction between the stars and the gas is so crucial.
Okay, break that down for me.
If you look at the stars in those elliptical galaxies, the primordial spin is completely gone. When the galaxies collided, the stars didn't actually hit each other, but their orbits got totally randomized by the chaotic gravity.
Like two swarms of bees crashing into each other.
Great analogy, yes. The stars are just moving in random, chaotic orbits. So the stars forgot the primordial spin entirely.
But the gas didn't.
The gas didn't. When the interstellar gas of two galaxies smashes together, it's a fluid. It physically crashes, heats up to millions of degrees, and violently mixes.
But wait, wouldn't a violent million-degree crash scramble the gas even more than the stars?
It seems like it should, but we have to remember the dark matter halo.
The invisible scaffolding around the galaxy.
Right. The visible galaxy is just a tiny glowing core sitting inside a massive invisible bubble of dark matter that extends way out into deep space.
And that dark matter halo is where the original tidal torque was applied in the early universe.
Right. Precisely. And because the halo is so huge, it's mostly insulated from the violent, chaotic crash happening right in the center where the visible galaxies are merging.
Oh, so the outer dark matter halo just keeps quietly spinning the way it always has?
It remembers the primordial torque. And here is where the magic happens. After the chaotic merger is over, you have all this superheated gas sloshing around.
Right.
But gas, unlike stars, can cool down. As it radiates energy away, it slowly falls back into the gravitational grip of that surviving dark matter halo.
It just settles down.
It settles down. And as it falls back in, it basically syncs up with the dark matter halo. It starts spinning to match the exact rotational velocity and axis of the dark matter.
Wow. So the chaotic merger actually destroyed all the local noise. And when the gas finally calmed down and settled, it aligned itself with the ancient, overarching rhythm of the universe.
Yes. The match between the gas's spin and the predicted primordial pattern was so strong it completely ruled out chance. This is the clearest evidence we have to date that today's galaxies genuinely carry an imprint from the universe's infancy.
So the primordial thread survived all that cosmic chaos. It just hid in the hot gas of massive ellipticals.
It survived. It doesn't mean spin is entirely predetermined, of course. Lots of galaxies lose that memory. But in these specific structures, the connection from the earliest tidal pushes to the modern day is right there.
Which is incredible on its own.
Mm-hmm.
But this surviving thread isn't just a fun fact about galaxy shapes, is it?
Not at all. It unlocks a completely new superpower for cosmologists.
Right, and this is where it gets really wild. Because tracing these primordial fingerprints gives us a brand new way to probe the invisible universe.
We can measure properties of the universe that are otherwise practically impossible to pin down.
Specifically, we're talking about neutrinos.
Neutrinos,
Yeah.
the ghost particles.
Now, neutrinos are incredibly elusive. Trillions of them are passing through your body right now as you listen to this, and you don't feel a thing.
They barely interact with normal matter at all, and they have almost zero mass.
So how on earth do neutrinos relate to the primordial spin of a galaxy?
Well, even though they have almost zero mass today, in the very early universe, they were incredibly abundant. They made up a significant fraction of the energy density.
Okay.
But unlike the cold, dark matter, which is sluggish and clumps together easily to form those lopsided potatoes, neutrinos were moving at near light speed.
So they were zipping around everywhere.
Yes, they're what we call hot dark matter. And because they were moving so fast, they didn't get trapped inside the forming clumps of cold, dark matter. They just blasted right through them.
So you have these heavy clumps forming and these ghost particles just shooting straight through the middle of them.
Exactly. And as they stream out of the dense regions and into the empty voids, their tiny little bit of mass exerts a very subtle gravitational pull.
A tiny collective tug.
Right. And that tug essentially smooths out the density of the early universe. It makes the clumps slightly less dense and the voids slightly less empty.
Wait, I want to make sure I'm picturing this right. If the neutrinos are smoothing out the clumps, they're basically softening those lopsided dark matter potatoes.
That's exactly what they're doing. They suppress the power of those initial fluctuations.
Okay, here's an analogy. It's like analyzing the unique spin of a tossed coin.
Okay, let's hear it.
By looking at the spin of the coin, you aren't just figuring out the exact lopsided push of the thumb that flicked it. You are calculating the exact density of the invisible air that the coin flew through.
Yes. The neutrinos are the invisible air. Because they smoothed out the lopsidedness of the dark matter, they weakened the tidal shear from the neighboring clumps.
Which means less torque was applied.
Exactly. A universe filled with a higher mass of fast-moving neutrinos will produce dark matter halos with slightly less angular momentum.
They spun up just a little bit slower because the ghost particles smoothed out the edges.
And because Sheng's team proved that we can accurately read the primordial spin from the hot gas in elliptical galaxies today,
Oh, wow.
we can measure that exact subtle deviation. We can see exactly how their angular momentum is missing.
And that missing spin tells us the mass of the neutrinos from the dawn of time.
Yes. We can detect the faint whispers of subatomic particles from billions of years ago just by looking at how gas rotates in a nearby galaxy today.
That is just, the scale of that
Yeah.
is almost impossible to comprehend. We are measuring the ghost particles of the Big Bang using entire galaxies as our scientific instruments.
It really is a profound realization. Everything is connected.
It is. What an epic journey. I mean, we started with the simple mystery of why galaxies spin.
Right.
And that led us to a primordial tug-of-war between lopsided clumps of dark matter and gas,
Then through the elusive project's computational time machine.
reconstructing the shattered glass, and finally finding the definitive proof, the surviving memory of the universe's first moments hiding in the hot gas of massive elliptical galaxies.
It really changes how you look at the sky.
It does. It leaves you with this lingering thought. If the chaotic, violent rotation of a massive galaxy, a structure billions of light years across, is still being quietly guided by the invisible, lopsided tugs of the primordial universe.
Yeah.
What other subtle, invisible forces from the deep past are secretly shaping the complex structures of our everyday lives right now? What are we doing today that was decided by a gentle push billions of years ago?
It's definitely something to ponder.
It really is. Thank you so much for joining us on this exploration today.
It was a pleasure.
We'll see you next time. Keep looking up.